Okay, so what we're basically doing in the next module is we're going to proceed to work our way down the formula sheet. We've previously talked about the reciprocal formulas and the quotient identities. But before we go further, I want to go in a little bit more detail about the reciprocal formulas and the quotient identities. In these particular identities, the powers follow. And I'll kind of show what I mean by that in just a second. You can use these formulas to evaluate and simplify trig functions. Okay, so that's the main intent of the formulas are to evaluate and simplify trig functions. As we get a little bit further into the course, you'll see that when we solve trig equations, okay, we're going to rely heavily on these quotient identities to simplify the trig equations and to evaluate. Okay, so first we want to take a look at the reciprocal and quotient identities. Okay, I'm going to bring up one note. And I'm going to turn off my phone. Okay, it does not want to turn off. Give me 1 second. It's supposed to be on silent. I don't know why it's not silent. All right. So I'm going to take a look at the reciprocal identities, and I just want to point one thing out. The powers do follow. For example, the sine of theta, that's equal to 1 divided by the cosecant of theta. And what I mean by the powers follow is that if we have sine squared theta, we could actually write sine squared theta as 1 divided by cosecant squared theta. Right? So if we're trying to substitute sine square, we can actually substitute sine square for 1 divided by cosecant square. Here's another example. We have that the tangent of theta is equal to the sine of theta divided by the cosine of theta. Let's say, for instance, we had tangent cube theta. We could rewrite tangent cube theta as sine cube theta over cosine cube theta. Right, so I want you to keep this in mind, which actually means that the formulas can be written in terms of powers. Now, they're not actually written like this on the formula sheet, but I just want to explain that they can be written like this. So, for example, the sine, okay, and I'm going to use the nth power of theta. That's equal to 1 divided by cosecant to the nth power theta. All right. I'm just going to kind of write all these things out. Cosine to the nth power theta is 1 divided by secant to the nth power theta. Right? So we were working with like a cosine to the 4th power theta. You can actually write that as 1 divided by secant to the 4th power theta. Tangent to the nth power theta is 1 divided by cotangent to the nth power theta. That can also be written as sine to the nth power theta over cosine to the nth power theta. Okay, and we're actually going to see some of these things as we work through the problems today. And then we have the reciprocals. Okay. So I'm actually going to bypass the reciprocals. I just want to show that the powers do follow when we're working with the reciprocal formulas and the quotient identities. Okay, I'm actually going to go back to some arithmetic for just a second, because in this first section, we're going to simplify some trig expressions, and we're going to be using some algebraic techniques. So you're going to see me write these formulas, and I just want everyone to know where these things are coming from. So here is a formula to simplify complex fractions. All right. For example, A divided by B, all divided by C divided by D. All right, and this is the setup for a complex fraction. So a complex fraction is basically a fraction, right? And we have the main fraction bar here. And in the numerator, there is a fraction. And in the denominator, there's a fraction. We can actually multiply the very top and the very bottom. And we can divide that by the bottom of the top and the top of the bottom. And I believe you've seen me use this before. So here is an example. And I'm actually looking for an example. Okay, well, I guess I'll forego an example, and we'll see this in action in an actual problem. All right, so this is one formula. That you've seen this one before. Now here's another formula, and it says that A divided by B plus C divided by D, right? Because we're also going to add fractions, right? Once we do some conversions, I can actually cross multiply A times D plus B times C all over B times D. Okay, you may or may not have seen this formula before. All right, and I'm going to modify this. This can actually be a plus or minus. All right, so here's a numerical example. Let's say we have 1/2 plus 2/5. All right, so I'm actually going to use a formula. So I have 1/2, 1 would represent A, 2 would represent B, and I have a plus C over D, right? 2 would represent C, and 5 would represent D. I can actually use this formula to quickly add the things together. Right, I can cross multiply. 1 times 5 is 5. I'm just going to actually write this out first, right? 1 times 5 is 5. That's actually the A times D plus B times C. So I have 2 times 2 divided by my denominators, B times D. Right, so 2 times 5. All right, so simplifying this out, we have 1 times 5 is 5 plus 2 times 2 is 4 over 2 times 5 is 10, which is 9 over 10. Right, you're going to see me utilize this formula as well. All right, now one thing just about this formula, when you have, and notice for my denominators, I have a 2 in the denominator and a 5 in the denominator. there are no common factors, right? The only factors are 2 are just 1 and 2. The only factors are 5 are just 1 and 5, right? So when there are no factors in common, we don't have to reduce, right? But if there are common factors, so let's say 1/2 plus 3/4, right? You're going to have to reduce in the end. So I'm going to use that same formula. So 1 times 4 is 4, plus 2 times 3 is 6, divided by 2 times 4, which is 8. So we have 10 over 8, and we have to reduce, right? Because we have some common factors in those denominators. So we can divide both 10 and 8 by 2. So we have 5/4. All right, we're going to see that in use today as well. All right, I'm going to go back to the formula sheet. All right, so we've talked about the reciprocal formulas and the quotient identities, right? And keep in mind that the powers do follow. Now we're going to talk about the Pythagorean identities. All right, so notice that we have sine squared theta plus cosine squared theta is equal to 1. Tangent squared theta plus 1 equal to secant squared theta. And then we have 1 plus cotangent squared theta is equal to cosecant squared theta. All right, now up until this course, the Pythagorean theorem has probably been written like this. Right, c squared is equal to a squared plus b squared. Right. So it's not like all of a sudden we're looking at this is our Pythagorean theorem, okay, or these are the Pythagorean theorems, right? So how are these things, I guess, formulated? All right, so we have c squared is equal to a squared plus b squared. Notice that when we talked about the Pythagorean theorem, we didn't use c, a, and b. We sort of used r squared is equal to x squared plus y squared. Right, so keep in mind this is like all within a unit circle. So let's just say we have, this would be r, right? This is our point on the circle. It has x comma y. We can drop a perpendicular. This is x, this is y, right? This is our right triangle, right? So instead of using c, a, and b, right, we're using r, x, and y. All right, so we've seen r squared is equal to x squared plus y squared, right? All right, so how are the Pythagorean theorems, right? Sine squared plus cosine squared equal to 1. So where does that actually come from? All right. So just keep in mind that the sine for some angle is y over r. The cosine for some angle is x over r. And the tangent of some angle is y over x. Right, so we've seen all of this earlier, right? R squared is equal to x squared plus y squared. R is equal to the square root of x squared plus y squared. X is equal to the square root of r squared minus y squared. And y is equal to the square root of r squared minus x squared. All right, so all of this should be familiar. All right, so here's where the sine, I'll do one of these. Right, so we're gonna see where this sine squared theta plus cosine squared theta equals 1. Where does it actually come in, and why is it considered to be a Pythagorean identity? All right, so we're going to start with the Pythagorean theorem. R squared is equal to x squared plus y squared. Now, keep in mind from algebra, whatever you do to one side of the equation, you must do the exact same thing to the other side of the equation. So what I'm going to do to this Pythagorean theorem is I'm going to divide both sides by r squared, right? So the property of equalities tell us whatever we do to one side, we do the same thing to the other. So we're going to divide both sides by r squared. All right, so let's see what happens. So I'm going to divide the left-hand side by r squared. I'm going to divide the right-hand side by r squared. All right. Now on the right-hand side, I'm going to go back to algebra. This probably was mentioned in Algebra 1. There's something, there's a theorem that says a divide by a monomial theorem. So dividing by a monomial means that we have a monomial in a denominator, right? And a monomial is a polynomial that just has one single term, right? So here was that. I'm going to just go over here. And here was the actual theorem: divide by a monomial. And it just basically says that if you have a plus b over c, you can write or simplify that as a over c plus b over c. And I'm going to use that divide by a monomial theorem on the right-hand side of this equation. All right, so we have r squared divided by r squared is equal to x squared over r squared plus y squared over r squared. All right, so the only thing I did thus far is just divide both sides by r squared. All right. So if we take a look at the number itself, is go ahead. I'm sorry. Did someone have a question? All right. All right, so if we look at the left-hand side, r squared divided by r squared is a 1. On the right-hand side, I have x squared over r squared. I'm going to kind of play a trick on that. I'm going to write it out as an exponent. I'm actually going to write it as x divided by y squared. Excuse me, x divided by r quantity squared plus y divided by r quantity squared. And if we look back at our relationships, x divided by r is actually cosine. So I have 1 is equal to cosine square theta. All right, looking back at our formulas, y over r is sine square. Right, and out pops that first Pythagorean identity. Right, cosine square plus sine squared is equal to 1. The other two identities, you can derive those by dividing both sides by x squared, right? That'll pop out one identity. And then if you divide both sides by y squared, that will pop out the other identity, right? But I want you to just show where these things are coming from. All right. There is also a Pythagorean identity sheet, and I want to explain what's going on this identity sheet. Okay, so here we have that first Pythagorean identity: sine square x plus cosine square x is equal to 1. And you see all of the derivations of this particular formula, which means that This Pythagorean identity, it can be solved for sine square, right? It can be solved for, and it's solved for sine squared here, right? Sine squared is equal to 1 minus cosine squared x. It can be solved for negative sine squared x, right? Negative sine squared x is equal to cosine squared x minus 1. It can be solved for cosine squared. It can be solved for negative cosine squared. It can be solved for positive 1. All right, it's already solved for positive 1. And it can also be solved for negative 1. Now, you're going to find in some of these instances when you're trying to simplify a trig equation or trig expression, you may have to rewrite, let's say, sine squared as 1 minus cosine squared. All right, now I'm going to admit there's a bit of trial and error in this, right? You can rewrite sine squared x as 1 divided by cosecant squared x using the reciprocal identities. You could also write it as 1 minus cosine squared x using the Pythagorean identities. Okay. So you're going to use whichever identity simply based on what you're trying to accomplish in your problem. Right? The same thing was done for the other two Pythagorean identities. Right? We have tangent squared x plus 1 is equal to secant squared x. Right? So here are all the derivations of that particular Pythagorean identity. And then lastly, we have 1 plus cotangent squared x is equal to cosecant squared x. All right, and we have all of the derivations for this particular formula. All right, so how do we use these formulas? Okay, so we're going to start off with the reciprocal and the quotient identities. All right, but before we do, I'm going to bring up the set of notes from section 9.1. All right, and on this first slide, it just gives some background information about trigonometric identities. And it just says that in 1831, Michael Faraday discovered a small electric current when a wire passed by a magnet. This phenomenon is known as Faraday's law. And we don't really do anything with Faraday's law in this course. It's just to explain the concept of where the trig identities kind of stem from in a practical application. It says this phenomenon is known as Faraday's law. This property is used to produce electricity by rotating thousands of wires near large electromagnets. Electric generators supply electricity to most homes at a rate of 60 cycles per second. Okay, so we talked about cycles and periods. This rotation causes AC current in wires and can be modeled by either a sine or a cosine function. All right, so here are the reciprocal identities. Once again, the quotient identities. Okay, here are the Pythagorean identities. And we talked about these negative number identities before. I couldn't quite find them, but here they are, right? In some instances, or not in some instances, whenever you're writing out the solution to a trig function, your angle measure has to be a positive angle measure, right? If you remember from the college algebra course when you were dealing with, I guess, exponents, the directions read, write all exponents as positive numbers. The same thing is true with trig. You want to rewrite all angles as positive angles. All right, so notice that in each one of these scenarios, we can take a negative angle and we can actually write it as a positive angle. Okay, so I'm going to skip a couple of slides. All right, and we're going to talk about verifying identities. Now, we don't actually verify identities per se. We will normally just simplify them. Okay, but there's some pretty good information on this particular slide. The first thing it says is to learn the fundamental identities. All right. And we don't actually verify identities. So what this verifying identity means is, just to show you an example. right? We have this trig equation, right? We have cotangent x plus 1 is equal to cosecant x times cosine x plus sine x. And what the goal is for this type of problem is you have to take the more complicated side and you have to write it as the less complicated side just to show that these things are equal. All right. So if you take a look at the slide, they took this more complicated side, right? And they've rewritten cosecant x is 1 divided by sine x, right? Then they kind of distributed 1 minus sine x. They combine the fractions, and then it's simplified to give you the left-hand side exactly. So we don't actually do this in this course, but the steps in actually going through this process are helpful. Okay. So it says it's often helpful to express all functions in terms of sine and cosine, and then simplify the result. So I'm going to bring up a problem. Okay, we're just kind of looking at a problem. All right, so if I just were to open up section 3.1 and we're taking a look at a problem and asks us to simplify the following expression, right, and we have secant x times cotangent x times tangent x, right, and we want to simplify. The first thing we should do is we should try to express everything in terms of sine and cosine. The fourth thing says that you can factor. Now this actually won't come in until we actually start solving trig equations. All right, but you can actually factor a trig equation or trig expression just as you can factor an algebraic expression. For example, sine squared theta plus 2 sine theta plus 1, that can actually be factored, right? That is equal to sine of theta plus 1 quantity squared, which means that if I were to take sine of theta plus 1 times itself, and if I were to multiply those two binomials, I would actually get sine squared theta plus 2 sine theta plus 1. You could also add trig expressions, right? So remember the formula we looked at earlier, a over b plus c over d, right? You can cross multiply. So you can multiply 1 times cosine. Oops. You can multiply sine times 1, right? So you get cosine theta plus sine theta in the numerator. And then you can multiply b times d, or you can multiply the denominators. All right, and we're going to see how that works. And we don't actually use the 5th and the 6th, okay, because we're not actually verifying identities. Okay, our main thing here is we want to write everything in terms of sine and cosine, right? A little bit later, we're going to be factoring. And also, we just keep in mind that we can add trig functions. All right, so let's take a look at some examples. All right, now I'm going to kind of clear my throat a bit. Now, I've been noticing something about these homework problems. They're supposed to be algorithmically generating new problems, but it seems like on some of these problems, it's just the same problem over and over and over again. All right, so I just want to kind of bring that up, and I'm noticing that about certain problems in the homework, they're not actually generating new problems. It just kind of gives you regurgitates the same problem over and over. All right, but nonetheless, let's take a look at a couple of examples. So here we're asked to simplify the following expression. We have secant x times cotangent x times the tangent of x. And then just notice in the problem that they give us recaps of the Pythagorean identities, the even and odd identities, the reciprocal identities, and also the quotient identities. All right, so the first thing we're going to do is we're going to simplify, and that was secant x times cotangent x times the tangent of x. All right. So in order to simplify, the first thing I'm going to do is rewrite everything in terms of sine and cosine. So I'm going to rewrite secant x, right? So remember from our reciprocal identities, the secant of x can be written as 1 divided by the cosine of x times the cotangent of x. All right, so keep in mind the cotangent, it can be written as 1 over the tangent, right? Just go back and just kind of show, right? It could be written as 1 over the tangent of x. But since we want to write everything in terms of sine and cosine, we're going to rewrite out the cotangent as cosine over sine. So I want to write the cotangent of x as the cosine of x divided by the sine of x. I'm going to write out the tangent of x as the sine of x divided by the cosine of x. And now we're going to simplify. So as we look at this problem, I see that I can cross cancel the cosines, and I can also cross cancel the sines. And that leaves us 1 divided by the cosine of x. And if we look at reciprocal identities, 1 divided by the cosine of x is equal to secant x. Right, so we have simplified we've simplified to secant x. All right, and I should use a set of parentheses around x. All right, so let's take a look at let's see. Number 5. All right, we're going to take a look at number 5. We have cotangent x divided by the tangent of x. So what I'm going to do at this point, I'm going to give you about 5 minutes or so to attempt to work the problem, and then we're going to come back with the solution. All right, so let's take a look at the solution. So it says write the following in terms of sine and cosine and simplify if possible. Your answer should only contain sine x and cosine x. All right. So we have cotangent x divided by tangent x. Okay, so we're going to rewrite everything in terms of sine and cosine. So I have a main fractional bar. And in the top, I'm going to rewrite cotangent x as cosine x over sine x. In the denominator, I'm going to write tangent x as sine x over cosine x. And now I'm going to use that formula that we talked about earlier. Right, I'm going to multiply the very top and the very bottom. So cosine x times cosine x is cosine squared x. And I'm going to multiply the bottom of the top and the top of the bottom. So sine x times sine x is sine squared x. And we have everything written in terms of cosine and sine. Right, so this is our solution. So that's cosine x squared divided by sine x squared. All right, so we changed everything to sine and cosine, and then we simplified. Let's take a look at number 6. All right, so here again, I'm going to give you about 5 minutes or so to attempt number 6, and then we're going to return with the solution. All right, so let's return with the solution. So we have sine x, cotangent x, plus cosine x. All right, so the first thing we're going to do is just write everything in terms of sine and cosine. So if we look at the first term, we have sine x, right, which is written in terms of sine. So I'm just going to bring that down, times cotangent x. So I'm going to rewrite cotangent x as cosine x divided by sine x. And I'm going to bring down cosine x. All right, so everything is written in terms of sine and cosine. Okay, for the first term, we have sine x times cosine x. So remember, when we multiply a whole number times a fraction, right, we can multiply the numerator, sine x times the numerator, right? So I'm going to write this out as sine x times cosine x over sine x plus cosine. I don't know how to stop the phone from ringing. I can stop my cell phone, but not the office phone. All right, sorry about that. How do you stop that? Okay. So now I'm going to simplify sine x times cosine x divided by sine x. We could cancel common factors. All right, so the sine x cancels. So I have cosine x plus cosine x. Right, so cosine x plus another cosine x would give us 2 cosine x. All right, so our solution here should be 2 cosine x. All right, so that's 2 cosine x. All right, so we have 2 times the cosine of x. Okay, that was number 6. All right, let's look at number 8. And I believe 8 is one of the problems that it doesn't actually change. The problem doesn't change. Okay, but nonetheless, I'm going to give you about 5 minutes or so to work out number 8, and then we're going to return with the solution. All right, let's take a look at the solution. All right, so we have tangent x sine x plus secant x times cosine squared x, right? And we're basically going to simplify. Okay, so we're going to write everything in terms of sine and cosine. So I'm going to rewrite tangent x as sine x divided by cosine x. I'm going to bring down sine x. I'm going to bring down plus. I'm going to rewrite secant x as 1 divided by cosine x. And I'm going to bring down cosine squared x. All right, so I have two terms. This is the first term and this is the second term. All right, so looking at the first term, right, I can't cancel anything. So I'm going to multiply sine x times sine x. So that's going to give us sine squared x divided by cosine x. For the second terms, notice I have a 1 divided by cosine x times cosine squared x. So I can actually cancel cosine x, and I can cancel one of the cosines from the cosine squared. Right, so that's going to leave us with cosine x. Now from this point, since my first term is a fraction and my second term is not a fraction, in these instances, fractions are our friends, right? So I'm going to just arbitrarily put cosine x over 1, and then I'm going to apply the formula that we were using. All right, so I'm going to multiply, and again, this is the formula I'm using. A over B plus C over D, that's A times D plus B times C over B times D. Right, so this is like A, B, C, and D. All right, so I'm going to cross multiply A times D, so sine squared x times 1 is sine squared x. Okay, so we're adding, so that's a plus. I'm going to cross multiply B times C. Right, cosine x times cosine x is cosine squared x. And I'm going to multiply the denominators. Cosine x times 1 is cosine x. All right. Now we can actually simplify this a little bit further. If you look closely at the numerator, we can substitute sine square x plus cosine square x. All right, if we take a look at that first Pythagorean identity, sine squared theta plus cosine squared theta is equal to 1. Therefore, we can substitute sine squared x plus cosine squared x for 1. I'm going to bring down cosine x. And from our reciprocal identities, 1 divided by cosine x is secant x. So just notice in this particular problem, it didn't ask us to write our final answer in terms of a sine or a cosine. All right, so instead of stopping to the point where everything was written in terms of sine and cosine, we went a little bit further, and we have secant x. All right. All right, I guess before we end class today, I want to jump into the next section and to just kind of touch on some things. All right, so we've kind of taken a look at that first block of formulas. Now we're going to take a look at the sum and difference of sine, the sum and difference of cosine, and the sum and difference of tangent. Now, if we look at this first group of formulas, the cosine of a sum or a difference, this first formula is written or is expressed as the sum of cosine. Right? The second formula is denoted as the difference of cosine. If we take a look at the sine formulas, this first formula is known as the sum of sine. The second formula is the difference of sine. And then we have the difference and the sum of the tangent. Okay. Now keep in mind that these formulas are used to find the exact values of the trig functions. All right, so here's what I mean by that. Okay, now as far as the way that these formulas are derived, I'm going to go back to the lecture notes section. And in section 9.2, and there's also a video for this sum and difference. There is a section 9.2 set of notes, and here is how the sum and difference formulas are derived. All right, so I won't go through this in entirety, but I kind of walk you through it. All right, so here's the setup. We have two angles. Kind of blow this up. There is an angle A, right? So notice that all of our angles start along the positive x-axis. So here is angle A, right? So here is the rotation for angle A. And then we have an angle B, right? So this is our angle B, right? So we have an angle A and an angle B. We also have an angle A minus B. All right, so the blue angle is the angle A minus B. All right, and then we have what are called chords. And a chord goes from one rim of the circle through the other, right? So we have R, S, Q, and P, right? And these things are just based on the terminal side for our three angles. All right, so P is the actual where the angles start. Q has the coordinates cosine B, sine B. So here is Q. All right, so this was our angle B. So remember that the first coordinate is cosine of your angle. The second coordinate is the sine of your angle. All right, so Q has the coordinates cosine B, sine B. S has the coordinates cosine A, sine A. So here is S, right? And that was the terminal side for angle A. So it has the coordinates cosine A, sine A. We also have R. R has the coordinates, the cosine of A minus B, right? So here is R, right? It's the terminal side for the A minus B angle. So it has a cosine of A minus B and a sine of A minus B. Okay. So it says that angle SOQ, so here we have SOQ is equal to A minus B. Since SOQ and POR, so here is POR, they're equal, right? We can set the chords equal to each other. So a chord, PR, so here we have PR, right? The length of this chord and the length of chord SQ are equal. Right? In order to find the length of these chords, we use the distance formula from algebra. All right, so here's what's kind of going on. We have PR, that's equal to SQ, as we just saw in the drawing. In order to find the length of PR, right, if I go back to PR, which is here, right, we can use that distance formula. Remember from algebra, the distance formula was the square root of x sub 2 minus x sub 1 plus y sub 2 minus y sub 1. And that's what we have here. But instead of using x sub 1 and x sub 2 and y sub 1 and y sub 2, they're actually using the cosine values, right? So the PR, its distance is here. That's equal to SQ, its distance is here. Once the square root is removed and it's solved for the cosine of A minus B, out pops the identity, right? This says that the difference of cosine, right, the cosine of A minus B, that's equal to the cosine of A times the cosine of B plus the sine of A times the sine of B. Right. And from this formula, we can derive the other sum and difference formulas. Right. So I'm going to kind of bypass on how these things are derived. And we're simply going to concentrate on the formulas and how to use them. All right, so when would you ever use formulas such as these? All right, I'm going to go into the next section. Section 3.2, and we're going to take a look at the very first problem, right? We're asked to find the exact value. And in this instance, we're given the cosine of 1/12 pi. All right, so first I'm going to figure out what pi over 12 is as an angle measure, or as a degree measure. So remember that pi is 180, and I'm going to divide that by 12, right? And we have 15 degrees, so we want the exact value for 15 degrees. Now, normally when we're finding exact values, we will use the unit circle. All right, so give me 1 second. I'm going to bring up the unit circle. All right. And lo and behold, we do not have a 15-degree angle measure. All right, so what do we do from this point? Well, if I were to put the cosine of 15 degrees in the calculator, just make sure that I'm in degree mode. All right, notice it's not giving me an exact value. It's giving me an approximated value. So here's where the sum and difference formulas come in. Now, even though I don't have a 15-degree angle, I can take two angles and subtract to get a 15. Right? I can take 45 minus 30, right? Because 45 minus 30 is 15. I can also subtract 60 minus 45. I can also get a 15 by using 135 minus 120. Right? And I'm bringing this up because it does not matter which angles you use, as long as in this case the difference is 15 degrees. Normally you want to use angles that are in the first quadrant, right? Normally because they're easy to work with. However, we can use the unit circle function values chart. Okay, we're going to see how this thing also kind of plays in on what we're doing. All right, so let's go back to our question. How can we find the exact value for the cosine of 15 degrees? All right. So first off, we started with the cosine of pi over 12. All right, from this point, I simply converted the radian measure to a degree measure. So we have the cosine of 15 degrees. All right, so when you're working with these sum or difference formulas, it's best to express the angle measure in degrees because the brain works best in degree measures. So now, how can I use a combination of the angle measures in the unit circle to get 15 degrees? Well, I'm going to use 45 and 30, right? So I'm going to rewrite the cosine of 15 degrees as the cosine of 45 degrees minus 30. All right. So I'm going to utilize the difference of cosine formula. Right, so right above the problem, I'm going to write the formula. So the formula says that the cosine of A minus B is equal to cosine A times cosine B plus sine A times sine B. So in this formula, we're going to substitute A for 45 degrees, and we're going to substitute B for 30 degrees. All right, so substituting those things in, we have the cosine of 45 degrees times the cosine of 30 degrees plus the sine of 45 degrees times the sine of 30 degrees. And the only thing we do from this point is we simply pull out the values for the trig functions and we add them. Okay, so if you look at your unit circle functions value sheet, all right, we can kind of quickly just pull out these values. So notice that the cosine of 45 degrees is square root of 2 over 2. The sine of 45 degrees is also square root of 2 over 2. And then we have the 30-degree angle. The cosine of 30 degrees is square root of 3 over 2. And the sine of 30 degrees is 1/2. Right, so we're going to write these values where they belong. So we have the cosine of 45 degrees is square root of 2 over 2 times the cosine of 30 degrees, which is square root of 3 over 2, plus the sine of 45 degrees is square root of 2 over 2 times the sine of 30 degrees, which is 1/2. All right, so we have two terms. This is our first term, and this is our second term. Now, keep in mind from algebra, right, the square root of 2 times the square root of 3, since we're dealing with square roots, we can multiply the radicand. So 2 times 3 is 6. So the square root of 3 times the square root of 2, that's the square root of 6. Keep in mind when you add fractions, you keep your common denominator. So I don't multiply 2 times 2 and get 4, right? I'm going to keep the common denominator. Well, excuse me, we're multiplying, not adding. So I would multiply my denominators. 2 times 2 is 4. Plus square root of 2 times 1 is square root of 2. 2 times 2 is 4. All right, so now we're to the point where we're adding fractions. We have a common denominator, so we keep the common denominator and we combine the numerators. Now I can't actually add the square root of 6 plus the square root of 2 because I don't have like radicands. Right, so what I'm saying is we can't actually add those to get a square root of 8. So this would be our simplest form, and this would be our solution. Now I'm just going to kind of check that with what we had earlier. Right, when we put in the cosine of 15 degrees, we got 0.96. So I'm just going to evaluate this in the calculator just to verify. So we have, I'm going to use the begin set of parentheses. We have square root of 6 plus the square root of 2. I'm going to close off my square root. I'm going to close off the numerator, divided by 4. Right, and we have the exact value. And another thing, you want to be careful putting these things in. So just notice in the calculator, I used a set of parentheses for the numerator. And you want to do the same thing when you're putting in your answers. So I'm going to hit a begin parenthesis for the numerator. All right, I'm going to put in the square root of 6 plus square root of 4. I'm going to close off the numerator. And we're going to divide by 4. And I'm sorry, that should be the square root of 2. All right, so notice I use a begin set of parentheses for the numerator. I believe if you don't use a set of parentheses, I think it'll mark it wrong. Let's see, S, and this is, by the way, this is one of the problems that doesn't change. SQRT of 6 plus the square root of 4 divided by 4. Okay, it kind of took it in that instance, but in order to be correct, I would use a set of parentheses because I found in some other problems that doesn't always work. All right, it'll kind of, oh, it did mark it wrong. All right, so notice that you should use a set of parentheses. Okay, I'm putting in the wrong numbers. Let me try that again. Okay, this is without a set of parentheses on the numerator. I believe it's going to mark it incorrect. All right, so notice without a set of parentheses, this is what we're actually writing. All right, so what it's doing is it's actually using the order operations, but what we want is to simplify the numerator, simplify the denominator, and then divide. All right, so it's going to be important to use a set of parentheses. I think my chances are up on this, but I think you all get the point. All right, so I think we're going to stop here. All right, I'm going to stop the recording.